raising those boards for him.
Thank you. And I notice he's only talking about polynomials with integer coefficients in one variable.
Yeah.
And that gives me a nice puzzle, which I really feel like saying, but anyway. So, I'm thinking of a polynomial.
Oh, that puzzle. That's a fun polynomial. Yeah. Oh, you are saying it. Oh, goodness, yes, this is great. Listen to John.
Okay, well, that's like certainly the strongest introduction I'll ever get from Dylan. So, I'm thinking of a polynomial which has non-negative integer coefficients. You're allowed to ask me questions of the form, what is this polynomial evaluated at x? For x, let's say algebraic numbers. You can't say, oh, what's p of pi, because then you know the polynomial. How many questions do you need to get the polynomial?
Is there a bound on the coefficients?
Well, they're greater than 0. No upper bound, no. And the follow-up question is, what if I do this in 2 or better yet k variables? Or an unknown number of variables where your inference have to be infinite sequences. But let's start with the one variable case.
I haven't seen the other one. The general version.
Depend on the degree of the polynomial?
You'd think, no. Sorry.
That's the degree of the polynomial factorial?
No. I said it does not depend on the degree of the polynomial.
In true BuzzFeed
yeah, I think you've seen it before, because I've kind of told this to everyone from Joburg.
In true BuzzFeed
no.
style, the answer might shock you.
The answer might shock you. So like this left column I've got for. Oh, never mind.
In fact, John's going to demonstrate. He's going to think of a polynomial.
Yeah, someone think of a polynomial. But if I demonstrate, they'll see it.
Okay, oh yeah, that's true.
Okay, tell you what, I will demonstrate at the end of class. So that you will be sufficiently distracted to not notice any mistakes I make. As I discuss Ramsey theory. Who's heard of Ramsey theory? Damn it. Okay, cool. Okay, so there's a famous problem which I think all of you probably know. 6 friends or people enter a room. Okay? Prove that there exist 3 all Facebook, TM, friends, or all not Facebook friends. Okay, so some will be friends with each other, some won't, but you know, there'll be a group of 3 who either are all friends with each other, or none of whom are friends with each other, within that group of 3. Okay, does everyone understand the problem? Anyone have any questions? Okay, who's seen this problem before? Who has not seen this problem before? Wow, okay, cool. So, maybe I should make it a little bit more... another way to think of this, each of these people is a dot. Just a tiny speck in the universe. But between them, and this is the same color. If they're friends, we draw a blue line. Okay, those people are friends. And if they're mortal enemies, we draw green. I mean, just not friends. Okay? So now, importantly, I have to fill in all 6 choose 2 lines, right? 6 choose 2 is 15, so quite a few of them. And what does this say? Either there's a blue triangle or there's a green triangle. Okay? Is that, everyone happy with that? Or that those 2 things are equivalent? Yes, no, maybe? Okay, so let's try. I can't fill this one in with blue, because then I'd have a blue triangle. right? So let's try green. And that means that this one has to be blue, because otherwise this would be a green triangle, right? That's totally allowed. Okay, and maybe this one. Well, I've done all of these 5, right? So let's say this one, we'll just do that. That'll have to be green. That'll have to be green. These 2 I haven't filled in yet. Let's make them green. And lo and behold, this is a green triangle. Okay, it took me a second to find it, but it's there. Okay, well, that's not a proof. Right, we've just shown that, look, we tried to construct something that doesn't work, and we failed. But maybe we could have been better about it. Okay, so the proof of this is to focus on a single person, who we'll call John. Okay? Okay, so now there are 5 other people here. Okay, and either John is going to know 3 of them, or he's not going to know 3 of them, right? This is a simple demonstration of the pigeonhole principle. Look, I have, 2 blues, 2 greens. I'm going to have a 3rd one, right? Okay, 3. Or maybe I have 3 blues, maybe I have 3 greens, but I'm going to have 3 of the same color. Everyone agree? Okay, so, Andy, okay, hello, Danielle. Okay, there are those 3. Now, there are 2 cases. If 2 of these people are green, we have a triangle, right? So each of them has to be blue. And that's also a triangle. So in either case, we're guaranteed to get a green triangle or a blue triangle. Yes? Okay. Well, can we do any better? What if we just have 5 people? Are we guaranteed a triangle? And the answer is no. Okay, and we have a pentagram, turns out to be free of monochrome triangles. Okay. Okay, so this leads to a more general theory, or more general problem called Ramsey numbers. I have a graph, and I'm going to color every edge either green or blue. Okay, usually I do red and blue, but we work with the pens we have. And I want to avoid either a K click that's blue or an L click that's green. Do you guys know what a click is? A click. In graph theory, a click is a group of n vertices, of k vertices, but it's a bunch of vertices and every pair is connected. Okay? So this is a 3 click. Is this a 4 click? No, but this is. Okay. And that's a 5 click. You guys get the idea. Okay, every pair is connected. and you don't want them to be monochrome. Okay? The question is, well, what we just showed is that R33, the 3-3 Ramsey number, this is defined as the smallest number of points we need before we're absolutely guaranteed either a green 3-click or a blue 3-click. Okay, that's 6. Why is it 6? Well, we showed that if it's 6, you have to have one, and we demonstrated that you can have 5 points and not have one, right?
Can I just ask about the notation, the 3 and 3?
Yes. So a 3-click is a triangle, right? So this does not have a red triangle or a blue triangle. Sorry, a green triangle or a blue triangle.
And is that called a Ramsey number?
This is called the Ramsey number 3-3, yes. Okay, so let's do a little bit of finding Ramsey numbers. What's the Ramsey number 1m? Okay, so you say 1. Anyone else? Yeah, it's 1. Okay, why is it 1? What does a green click, what's a click of size 1 look like? It's just a dot. It's one guy, and everyone else in the click, which means absolutely no one, there's a green light, sure, it's 1. Okay, and of course that's equal to R M1. Okay, by symmetry. Okay, what about R 2m? Okay, what does this mean? Well, either you've got a green line between two people, or you have a click of m blue things. Well, if you have m things, you're kind of guaranteed that, right? Because either everyone knows or doesn't know each other, depending on which way around you do it. Or, well, either everyone knows each other, or there are these two people who don't. And if two people don't, or everyone does, m. So does anyone know, or can anyone see the formula for R3m? Okay, the answer is no. No one can.
Yeah.
So, in fact, I don't know if you quite get a feels medal for finding a general formula, but you wouldn't be that far off. Okay, so R 3, 3, 6, R 3, 4, nine. Okay, these numbers aren't that big, but if I've got 14 points, I've got 14 choose 2, which is 91 lines between them, and 2 to the 91 colorings. Granted with some symmetry, but 2 to the 91 is often thought of as big.
Yeah.
So checking everything is hard.
Context.
Okay, R 3, 9, I'll jump to, is 36. R 3, 10 is open. Okay, we don't know what it is. We know it lives somewhere in the range 40 to 42. May all your IMO scores be there. Okay, but that's the, we can't even tell, we don't even know the answer to this case. But, maybe it gets better for 4. No. Okay, R 4, 4, 18. R 4, 5, 25. Okay, and someone got tenure somewhere from finding this. And R 4, 6. is somewhere in the range 31, is another open one. Okay, and I know this is kind of showing cases. Okay, R55 is also open. And we know it's between 43 and 48. Okay, again, 2 to the 48, choose 2. Good luck checking all of them. Now, Uros had a quote about this. Imagine some really powerful alien show up tomorrow, and they say to us, guys, you've got 1 year, and we need to know what R55 is, or we're just destroying you. So what do we do? In that case, he thinks, if we put all our mathematicians and all our computers into solving it, yeah, we should do that, and maybe we'd survive. If they ask for R66, put all that effort into destroying the aliens, that we'd have no chance. I just bet that, we might do better by going, yeah, we don't think you know either, so, and just taking a guess somewhere in our range. Okay, so now let's get on to some actual math about this. Okay, so it's not actually obvious at first glance whether Ramsey numbers always exist, right? If I have 1 million dots, is it really obvious that I need to get a 10 blue click or a 10 red click? Up front, not really, right? Quite possibly, this doesn't happen. But Ramsey was very smart, so it does. And here's the relation. Ramsey says, look, R and N is bounded above by R n minus 1n plus R n minus 1. Okay, how do we prove that? Some kind of induction. Sort of. Okay, so we use the same technique that we've used on 6 people. We take this one guy, and we say, hey, imagine if there are R m minus 1 n people here, and then another group of R n minus 1, right? Well, if we had that many people, we'd be guaranteed to get at least one of them, right? And in fact, even if we have one less person, we're guaranteed to either have this many blues or this many reds, right? Guys? But by the same argument here. Right, imagine you know that R9, well, let's say we're looking for R10, 100, right? Well, if we know R9, 100, and we know R10, 99, add those two together, subtract 1. Look at this whole group, throw reds and blues at them, and you're guaranteed that either you'll hit this many reds or this many blues. And that gives us this result. Any questions? Okay, can't tell if that's board or lost, but let's go. And this tells us that, yeah, Ramsey numbers always exist. Okay, so in particular, Mn is bounded above by a nice binomial coefficient. How are we going to prove this? Induction. Okay, we're going to use induction. Okay, so base case, we know our 1m is our m1 is 1, which turns out to be m plus 1 minus 2 m minus 1. Okay, so base case, if we have a 1 anywhere, we're good. Everyone happy? Okay, now, I guess this is a mn. 6, and we have a whole bunch of ticks. Okay, I do need to be a little bit careful here. And now we can imagine we're at a point where this and we're on both sides, we're good, right? Okay, well, we know our mn less than okay, so this is m minus 1 minus n minus 2 minus 1 minus 1 m plus n minus 1. Okay. This is by the inductive hypothesis. Okay, and by the recursive property of binomial coefficients, okay, you guys, you're all happy with these two rows add up to this thing in binomial coefficients? Yeah? Okay. Cool. So by induction, we get that if I've got these two, I'm good. So, cool. Goes like that, and then goes like that. And this 2 deduction works. Everyone okay with that? Okay, so that gives us an upper bound on Ramsey numbers. Okay, how about a lower bound? Okay, so for this we're going to use the probabilistic method. Has everyone seen this? Probably not. So here's the idea of the probabilistic method. You have some big complicated terrifying structure like this, and you say, well, what would happen if I kind of picked a random one? And you say, well, on average I'd get 0.92 of these. That means there must exist some which have none of these. Let's be a little bit more clear. So imagine I have RR, okay? Central Ramsey number. Okay. This is going to be online, by the way. Okay, cool. No stress. Just heads up. Okay, so I would find RR, and I've got n points. Okay, how many? If I just color things at random, how many colorings do I expect? Okay, what's the probability an individual R points are monochromatic? Okay, well, how many in R points, there are R choose 2 colorings, and 2 of them are going to be, 2 of them are going to be monochrome, right? They're all red and they're all blue. Yes? And we're going to have N choose R such sets of R points. Yes? Okay, so conditioned on this being less than 1, there might be times when, in fact, these things are dependent on each other, but there might be times when more than one coloring is monochromatic. That's great because as long as these probabilities aren't enough to tile the whole thing, that's still positive. That still means it's less than 1. And we do some algebra, we use Stirling's approximation, and we get that R of RR okay. And we showed that it's less than that binomial coefficient, which can also be approximated. Yes?
Yes, it's always less than 1. Can't it be sometimes like equal to 1 here?
Equal to 1 is a stronger condition.
Yeah.
And because we have dependence, it's probably good enough here. In general, you'd have to sort of make some argument, and I'm sure you can make it here, about second moments. The point is that you need, so if you have a probability space of size 1, the probability of this particular coloring being monochrome is this number over here. So you're putting it down, take another probability, also put it down, maybe it intersects a bit, but possibly it doesn't. And you tile the whole thing. And then the idea is you have a little bit of space left over where nothing is monochromatic, and therefore you have a lower bound. Emmanuel, you had a question?
For that lower bound, we look for a zero case of FM.
You can. So I guess what you have to do then, you can, but it gets a bit more complicated because you sort of have to go, well, you just have to break this into the reds and the blues. But yeah, the same argument holds. So what we get is this. Less than okay, so we do have some bounds on Ramsey numbers in general, or on central Ramsey numbers at least. Now, for R equal to 10, these bounds are 101 less than R, 1010 less than 48,620, but it's a bound. Okay, so that shows sort of how hard this problem can get. Okay, so, well, it's all very well when people are Facebook friends or not, and when we have 2 colors, but what if we've got 3 colors? Yes, these things get worse. So here's a question which I think was on an IMO once. 17 professors correspond with each other on the subjects of mathematics, physics, and chemistry. And each pair of professors only talk about one subject. And can you prove that there are 3 of them that all talk about the same subject with each other? Okay, and of course this generalizes to, so right here, let's do that.
How many professors would we have?
17. same argument, which is basically the only one we have in random theory. Okay, think of one professor. John, could be you again. You got promoted. Okay, well, there's 16 other people. So blue, green, or black. Okay, he has to be talking to 6 people about one or the other of these subjects, right? Like there's 16, he breaks them into groups of 3, 5 plus 5 plus 5 is 15, okay, cool. Maybe he talks to 6 about the black subject. I'll let you decide which one that is. Chemistry. Okay, these 6 people, if any 2 of them talk about chemistry, we're done, right? Because then that's a chemistry triangle. But if they all talk about blue and green, math and physics, well, the 6 of them, we've shown that we have a blue-green triangle. Right? Okay, so R through 3 to 17. And I just kind of lied. Why did I lie?
You didn't prove that that's the lowest.
Yeah. So maybe it's true that for 16 people, you're also forced to have a triangle. Turns out it's not 16 people, you can find a construction. I'm not going to show you that construction, but when we're proving things, it's a good idea to be careful about this. So we worked. So next question. What if professors talk about 4 subjects? Math, physics, let's do computer science and statistics and 6 mathematical subjects. And it turns out if you have 66 graphs, you can make the same argument. Right? Because he's talking to 65 people. There have to be 17 of color 1. This guy of 17, none of these 17, none of them can talk about the same subject. So that goes to 6 and 1, which goes to thing, and there's the equal 66. And I'm not sure, but I think that with this family, that actually there is a construction which works for sort of a general 3. I could be wrong about that. Okay, so I have one more fun problem for you. Did anyone solve my polynomial question? No, don't worry.
I'm thinking of a polynomial.
Oh, you're thinking of a polynomial?
Yes.
Well, okay, I want to give them another problem though. Which means I should actually, you know what? Cool. You're thinking of a polynomial, Dylan.
Yes.
What is your polynomial for evaluated at 1?
It is 12, John.
It is 12.
Yes, it is.
Ah. And what is it evaluated at 100?
My polynomial at 100, John.
Yes, your polynomial at 100, Dylan.
It is 20,307.
You say it's 20,307?
I do indeed.
Right. In that case, is it 2x squared plus 3x plus 7, Dylan?
How did you know that? That's amazing.
Yes, it is. And I think that will pick up how you do this, right? Yes?
What about fourth degree polynomial?
Sorry?
About fourth degree.
Well, do you have a 4th degree polynomial in mind, Farron?
Yes.
Ah, excellent. What is the polynomial evaluated at 1, Farron? Okay, I do want to give them a nice Ramsey theory problem though.
Okay.
But I think that you'll need the mind to think about it.
Yeah.
58. I'm double checking.
Really? Really? Okay. So, you say that your polynomial evaluated at 1 is 58 farad?
Yes.
Well, what is it evaluated at 100? You should be able to just read this out, just write this out. Okay, while Farron is thinking about it, let me ask you another question. So I'm going to have the real numbers, but let's just say the numbers between 0 and 1. Okay? And each of them is a person. And some of them are friends and some of them are not, and some of them are type 1 friends, some of them are type 2 friends, some of them are type 3 friends, and so on. But there's, we're going to put in an edge between each of them, right? And we will use countably many colors on them. Color 1, color 2, color 3, and so on. And can you avoid a monochromatic triangle in this world?
Wait, say that again.
Just start again and just say it slow.
Okay, so we have a coloring with countably many colors on edges between real numbers in the set 0, 1. Okay?
Yeah.
Can you construct such a coloring which does not have a monochromatic triangle? Okay, well, you might not be able to, but maybe someone else can.
That sounds impossible to solve.
Okay, well, if anyone solves it,
Every pair of
real numbers, there's an edge between of some color, which could be color 1, color 2, color 5,786. What's your polynomial?
You need to add 100.
Yes.
2073.
What? 2073.
11.
11.
305.
You're a liar. Well, maybe you're not. So it's 5, 13x, 31x squared, 7x cubed, 2x to the 4.
Do you use the P of 1 to figure out 110?
Yes.
How you
Yeah. So you don't actually need a power of 10. You just need a number that's bigger than any of the individual coefficients. And it will
Did you
separate out.
specify positive coefficients?
Not negative.
Yeah, okay.
Okay, yeah. So, yeah. So you just need an upper bound on the coefficients, because otherwise you could get a spillover. And I'm sorry, I thought there was a 73. I was wrong about that. Take it back. Okay. So you don't want spillover. What is at least as big as any of the coefficients? Well, there's some which you can get by asking at 1. And then you ask for a power of 10 because then it just reads off. Now, I once had someone in undergrad take out their calculator and tell me that no, my trick didn't work, you can just calculate around it. This was not the smartest cherry in the group. Okay, so you guys should solve my infinite Ramsey theory problem. You should also solve this for n variables. If anyone gets those, I'll buy you up to 1 chocolate. And only for the first person, because let's be honest, otherwise, like the first person solves everyone. Yes, Darren?
Right up to 1 chocolate.
1 chocolate. Well, possibly 0.
I'd say.
Yeah, I'm gonna limit like the amount of damage I can do myself to 1.
Did you say finitely many colors?
Countably many colors. Yeah. So countably infinite.
This can be counted.
Yeah, you can have color. You can have any color indexed by the naturals.
I don't think so.
Can you prove it?
No. But there's just too many things.
Do you know how many
Oh,
numbers
come on,
there
there
are
are only
between
like-
0 and 1?
Or is it the?
I'll give you a clue.
Out of
You
1
know
to
how many
11.
numbers there are between 0 and 2?
Infinity.
But surely it's like
since the Ramsey number always exists, the whole point.
Sorry?
Isn't it just like the Ramsey numbers always exist and just
Yes, but when is the Ramsey number
Doesn't
comfortable
generalize to
infinity and
infinities.
uncomfortable
Because it's
infinity?
like, if you take the limit, it might not.
Yeah, so the question is the Ramsey number for uncountably infinite sets
Even well.
for okay, is R33333 with infinitely many threes, uncountably many threes, greater or smaller than 2 to the, well, in the content of the reals. By the way, I once asked some math overflow if this is if you can avoid all cycles, just and give it away, and got told that that's equivalent to the continuum hypothesis.
Nice.
Anyway, Andrew, over to you.
It's showing you either open or
It is not open. It is neither open nor does it involve the axiom of choice.
Oh, really? Okay.
The fact that you weren't willing to bet more than one chocolate and convicted might not be open.
Okay, if it was open, I would be willing to give you 2 chocolates.
On top of this,